Okay, so here we have a problem just like we had in class. So we're going to start off doing this problem just as kind of a warm-up for what's to come. So we got FB equals QVB sine theta. Now, if you read the question, it says 8 microcoulomb object moves through a 5 Tesla magnetic field, feels a force of 1600 newtons. What is the velocity? So we know the force, gave it to you, it's 1600 newtons. The charge is 8 microcoulombs, so hopefully remember micro is 10 to the negative 6 coulombs. We're looking for V. And we have the magnetic field of 5 Teslas. Lastly, remembering that the angle is the angle between the magnetic field, which in this case is in the negative z direction, and the velocity, which is in the positive x direction. And with very little convincing on your part, I'm sure you can convince yourself that's 90 degrees. Okay, so this goes away. We do the rest of the necessary algebra, and I'll give you a second or two to figure this one out. Should be 4 times 10 to the 7th meters per second. Okay, so fairly straightforward. Now, we have to also remember that if you look at the way this is moving, still trying to get used to this stylus here. Sorry about that. Okay, so if we look at the way this particle is moving as it enters, we're going to assume for later that this is a negative 8 microcoulomb charge. So using our left hand rule, we'd have our fingers into the board. We'd have our thumb facing to the right, and that would leave our palm or our F finger facing down. So that's the direction the force due to the magnetic field would be, and that's why you notice it curves, because remember that force is going to act somewhat like or exactly as a centripetal force. Okay? Now, here's the next situation. This is kind of an application of what we've already done. So you look, and now what we're going to do is we're going to talk about, instead of just a single particle, we're going to talk about a current. So there's going to be a current, which, remember, is just a whole bunch of, we're going to say electrons, because we all know that that's actually what's happening. It's a whole bunch of electrons moving to the right in this wire. Okay, now, if I have a single electron moving that way, then just as we had before, since this is a negative particle and the velocity is in this direction, we know that the force should be downward. Now, we can also note that if there's a current flowing, there's a whole bunch of electrons in here, right? So, we go back to this color. So there's a whole bunch of other electrons in here, all moving in the same mass direction, all therefore feeling individual little forces. Okay, so how do we make our formula kind of show the same thing? Go from this somewhat microscopic look at things to more of a macroscopic look at things. Well, what we're going to do is we're going to first look at this as the length of the wire. Okay, so we're going to say FB is equal to Q. Now, velocity of each individual particle in here would be the distance it traveled over time, B sine theta. Okay, now this can be written a little bit differently. If we take the t, and algebra allows us to do this, put it over here, we're going to let d be the length of the wire, right? Because that's the distance it's traveling during that length of time. B sine theta. So now we have FB equals Q over T is our old friend I, just a current, which is helpful because it's something that's fairly easily measured. L, B, sine theta. So what we have here is we have a formula that's kind of more of a macroscopic look at if you have a current flowing through some length of wire that's in a magnetic field. And we know the angle between, in this case, the current now and the magnetic field. We can find out how much force would be acting on that entire wire as opposed to on each individual little particle. Okay, so let's just do a real quick example. So we have a 2 milliamp current. It's passed through a 20 centimeter long wire in a 4 microtesla magnetic field. What force would the wire feel? All right, so draw the wire real quick. Just sticking with, I guess, the same way we've been doing this. We'll allow the current to be flowing this way, the magnetic field to be flowing into the board. So now we have to be a little bit tricky because remember, if we're going to do this, and this is, let's say, an AP question, the current is not the flow of electrons, but instead is the flow of positive charge. So we're going to use our right hand here. And since we have magnetic field into the board, our fingers are facing into the board. Our thumb is facing the direction of the current or the velocity of each individual particle. And that would leave our palm facing upwards. So before we do any calculations, we can say, we could say that we know that the force acting on this wire would be upwards. Okay, so now we go back to our pen. Let's do the calculations. Now we got FB equals, now 2 milliamps, so remembering that this is 2 times 10 to the negative 3 amps. L, well, it's 20 centimeters, so that's going to be, remember, 0.2 meters, because everything has to be in SI units. 4 microtesla, so of course we're going to run out of room here, go figure. Let's bring this down here. Okay, goes back to our pen. So this is, again, 4 microtesla, remembering that micro is 10 to the negative 6 Tesla. And our angle is still going to be 90 degrees. So it's going to be sine 90, which we can write, or not, because we all know it's going to be 1. So this becomes 2 times 10 to the negative 3, 4 times 10 to the negative 6. So already that's going to be 8 times 10 to the negative 9 times 0.2 is just going to give us 1.6 times 10 to the negative 9 units. Now, as always, I would say you can check my math on that because I just did that in my head, so hopefully we're right. So, why is this important? What great applications come from this? Well, hold on, let's go to the next page. All right, so this is basically the principle behind 2 major things. One would be this picture below, which I'll explain in a second. It's the electric motor. So basically what a motor does is it takes electric current and it passes it through a loop in a magnetic field. And in doing so, it creates a force. But because this is a loop, it's going to create a torque. So as you can see here, it creates a torque in that direction. Now, just before we move on from this, let's talk about why this is actually happening. If we look at, let me just change the colors for emphasis purposes. If we look at this side, in this side we have a current flowing this way. Okay, so if the current is flowing that way, we could say that the particles are moving that way. So if the particles are moving up, our thumb would be facing up, right? Now, we're using our right hand. So our fingers, according to the picture, and I know it's hard because it's 3-dimensional, our picture shows the magnetic field is going from the north side to the south side, which it always does. So it's going to be going to the right. So if you put your fingers to the right, I assume you guys are all doing this, probably at your kitchen table, and your family's probably making fun of you, but it is what it is. So your fingers are to the right, the current is up, so your thumb is going to be facing up, and that would mean that on the left-hand side, the one that I've circled, the force would be into the board, which is the direction they're showing right here. Now, because this is kind of pivoted along the middle here, a force this way is going to start to make this thing torque in that direction. Now, oh, hold on. Now, this side is basically the same principle. You got a current this way. So now if you line your fingers up so that they're going to the right of the page, right, with your right hand, remember, because we're doing AP current, the stupid current, right? And now you have to twist your hand over. Then your palm would be facing out. Your palm would be facing out of the board, so you'd be facing this way, right? So if it's facing that way, it's going to be creating a torque also in the same direction. So you have forces in opposing directions, but the nice thing is they're both, when we go to rotational stuff, creating a torque in the same direction. So very, very cool, right? Now, you might have a question about this side. So let's erase again. This side here, the current will be flowing this way. Now, if you remember correctly, if the current is flowing in that direction and the magnetic field is basically moving in that same exact plane, the angle between those would be, well, 0. And that means that there is no net force due to the magnetic field on this portion, nor this portion, nor that portion. And these you wouldn't have to worry about because one would argue if it's a well-made motor, those won't be in the magnetic field. So, pretty cool. This is how an electric motor works. It's taking electric current and it's making it into actual physical motion. Now, this diagram might not be quite as good, but in this picture, it's the exact opposite. So what's happening here is we are going to move the wire, physically move the wire this way. Now, that means that each individual little electron is moving downward. Physically, we are physically pulling this wire, right? Now, if I physically pull this wire, that's the direction of the velocity of each of these. So if I put my thumb facing downward, and I know that my magnetic field, according to this picture again, is going from north to south, so this way, right? So if my velocity is down, right, and my fingers are going to be going from left to right, and they're talking about electron flow here, so they're going with actual real current. We'll talk about how to do that with the positive current in a second. So I'm going to use my left hand. My fingers are to the right. My velocity is down, right, because the wire is being pushed downward. And each individual electron in there, hold on, we'll change colors just to emphasize this a little bit. Each individual electron in there would be getting pushed that way. And that would end up creating a flow of electric charge. Now, if you did it the other way, you did your hands using the right hand, everything else the same, it would just show a current flowing this way. But if you're using the opposite hand, that would be a current flowing that way of positive charges, which kind of makes sense. So the cool thing about this is this shows you another very important device in electricity, which would be the generator, right? What does a generator do? A generator takes a piece of wire or many coils of wire and moves them physically using a motor through, or whether it be a motor or a turbine of some kind, whether you're doing, water power or anything like that, and it moves it physically through a magnetic field. And when it takes that thing and moves it through a magnetic field, it gets electrons flowing, which is a current. So, two really, really important parts of this. Okay? Now, I know that this seems short, but the whole idea was to make sure that A, my technology abilities were up to the, up to the task, which I guess that'll be for you guys to decide. And also just to make sure that I got something out there that was a reasonably simple thing. Now, here's my last slide. It has nothing to do with physics necessarily. Here's what I'm looking to do for the rest of the week. And I always try to do this while we're in class to give you an idea what's coming. So I figure why not do it now also? So what I'm hoping to accomplish before the end of the weekend, and it, will depend on how much time I have to get things done, I'm looking to set up live links as for the reference material. These will be on your Google Classroom. So I will set up Google Classroom links, or I'll set up somewhere on the Google Classroom, whether it be in just the feed or under assignments or something along those lines. I will set this up for you. I have been looking into different formats for this. What I'm going to do with this most likely is do some sort of a Zoom call. We'll decide on a kind of a mutually agreeable time for all of us, at least one time a week for me to get together, and if nothing else, just kind of have a recitation period where we get to talk about the assignments I've assigned. And I'm looking as to how to figure this out. Interactive homework assignments. So basically, instead of me just giving you something and hoping you're doing it, I can actually have you submit it, and I could check it and even leave notes and such. And I know it's all possible, but you guys all know my technology abilities, so we're learning here, all right? Lastly, if you have any questions, you can obviously contact me on my school email address. You can go through the Google Classroom, and please note what I put in parentheses there. Here's my cell phone number. If you need it, if you have any questions, all I ask is that you be respectful, because I am home with my family at the moment. So if you have any questions, please don't call me at 10:30, 11 o'clock at night, which I know sometimes you guys are up, but I will not be. I will be out cold. All right, well, hopefully that was helpful. Hopefully this is going to work for us, and, I'll talk to you guys next time I make a video.